So today we are dealing with the subject nuclei. So in this one there is a first introduction. An atom consists of a positively charged nucleus with surrounding by electrons, and the size of the nuclei is less compared to the size of atom. Nuclei consists of protons and neutrons. So protons and neutrons are there with the nuclei. So total number of protons gives atomic number Z. Atomic number Z for that particular atom. Next one is total number of protons plus neutrons gives mass number. We give it as mass number A. Now, what is 1 AMU? So, it is a unit, atomic mass unit, that is given as 1 by 12 the mass of carbon. And its value is approximately 1.67 into 10 power minus 27 kgs. About the discovery of neutron. The discovery of neutron was done by James Chadwick. An experiment is there for this. So, it is a polonium source. Gives rise to the source of alpha particles. Then it is allowed to fall on substance like beryllium. This gives rise to uncharged radiation. Which is allowed to fall on a paraffin-like material which contains most of the proton in it, and this radiation was detected by means of a GM counter. So when this uncharged radiation was detected, they found a neutral particle, that is nothing but a neutron. So this is the experiment that led to the basis of discovery of neutron. There are properties for neutron. So neutron, it does not have charge, but its mass is 2000 times the mass of electron. That is first property. Next, second property is it is not deflected by electric and magnetic fields. Third property is the ionizing power is less, but the penetrating power is more. And the lifetime of the neutron is approximately 1000 seconds. So these are some of the properties of neutrons. Mass of neutron 1.0078 AMU. Mass of proton it is. Mass of electron 0.00055 AMU. Mass of neutron 1.0087 AMU. So these are the masses. Now we come to the size of the nucleus. So size of the nucleus. So before speaking the size of the nucleus, we have the formula mass by volume is equal to density. Mass by volume is equal to density. So you can write it as mass is equal to density into volume. So mass is directly proportional to volume. So you can write this as mass directly proportional to means volume means it is nothing spherical in shape. So 4 by 3 pi upon pi r cubed, where r is the radius. Now here there is a special relation here. So is equal to r naught a power 1 by 3. So r naught value is a constant that is given by 1.4 into 10 power minus 15 meters. So this is a special relation between the radius and mass number. There you can calculate the ratio of radii. There is a problem on this. The masses are, or atomic masses are 27, 64. Calculate the ratio of the two atoms, radii. So here we can write it as r is equal to r naught a power 1 by 3. So we have to calculate the ratios. So r1 proportional to a power 1 by 3 or r2 proportional to a power 1 by 3. So here r1 by r2 is equal to here a1 upon a2 whole power 1 by 3. So they are asking you to calculate the radii. So this becomes, so r1 by r2 is equal to a1, so 27 by 64 whole power 1 by 3. So r1 by r2 is equal to, it gives 3, so 27 cube means it is 3 by 8. So the ratio is 3:8. So this is a problem on the ratio atomic radii. So mass defect is known as the total mass of the nucleus is always less than the total mass that is formed by the protons and the neutrons that are held together. So it is given by delta m equal z into mp plus a minus z into mn minus actual mass of the nucleus. So z is atomic number, mp is mass of proton, a minus z gives the number of neutrons, mn is mass of neutron, and M nucleus is the actual mass. Now the mass of the proton is 1.0073 or approximately 1.0078 AMU. Mass of the neutron is 1.0087 AMU. Now, effect for carbon atom, carbon. So delta M is equal to, this is nothing but carbon 12 upon 6. So delta M is equal to 6 into 1.0073, or it may be 7873 plus A minus Z means 6 into 1.0087 minus actual mass is 12 minus 12. So it comes about approximately around 0.0978 AMU. This is nothing but atomic mass unit, delta M. And when 1 AMU of energy of mass defect is there, how much energy is released? It is 931.5 MeV or 931.5 into 10 power 6 eV. So this is how the energy, the mass defect is being calculated for carbon atom. It is the amount of energy released in the formation of the nucleus. And its value is given by delta M into C square. Next, there is another energy, binding energy per nucleon. So it is given by delta E by total number of nucleons in the nucleus. And there is a graph for explanation of this binding energy per nucleon. This is the binding energy curve. So here we take mass number, that is A, and this is the binding energy per nucleon. So it comes out to be like this. Now, this is known as binding energy curve. So, there are some points for this. The maximum binding energy is observed for iron. it is approximately 8.75 MeV. For iron, 56. This is the first point. Second point is it is approximately around 7.8 MeV for uranium. And from A is equal to 30 to A is equal to 170, the binding energy per nucleon or EBN is constant. And fourth point is for A less than 30 and A greater than 170, the binding energy is nearly very low. So very less it is. Are the 4 points that are to be noted. So it is highest. So when it is very low, it shows that they are unstable nuclei. Means lot of them they are supposed to be some radioactive materials. This is known as the binding energy curve. And these are some of the points to be noted for this binding energy curve. So radioactivity means when a nuclei is unstable, it emits alpha, beta and gamma radiations. So everywhere, almost all, the radioactive nuclei are supposed to undergo this radioactivity. And the unit of radioactivity is Curie. So this is how radioactivity, there is an equation for this here. Let us suppose N is the number of atoms. So with time they decay. So dN by dt. So these are the atoms that have decayed. And the atoms that have decayed are proportional to N, the total number of atoms that are present initially. So dN by dt is equal to a constant sum K or lambda into N, where lambda is known as disintegration constant. So I put a minus sign before it because number of atoms decreases. So dN by dt is equal to minus lambda upon N. So I integrate the equation. Integral dN by N is equal to minus lambda into T. So for this integration, this equation, I take dN by N is log N. So here I take N0 and N to be the two limits. Integral N0 to N. So this equals to minus lambda into, so this dt goes over here. So minus lambda into T. Or I take this as, so if I substitute the limits, log N minus log N0 is equal to minus lambda into T. Or this we can take it as log N by N0, the base E is equal to minus lambda into T. Or N is equal to N0 e power minus lambda into T. So this is the expression. So N0 is the initial number of atoms and N is the total number of atoms. Integration law. Now I represent it by means of a graph. Time period T, number of atoms, this is N0. So N0 by 2, N0 by 4, N0 by 8. So this is T half, this is 2T half, and this is 3T half. So this is represented by means of a graph. So N0 by 2 means it is T half. Again half of that is means 2T half. Again N0 by 8 means it is third half period. Between disintegration constant and half-life period. So we have this relation n is equal to n0 e power minus lambda into t. So n we write it as n0 by 2 is equal to n0 e power minus lambda into t. So with t half. So n0 gets cancelled, or lambda is equal to 0.693 by t half. So this is the relation between disintegration constant and half-life period. Next one is, what is alpha radiation? So suppose I take alpha radiation. Suppose I take a nuclei X with mass number A and Z is the atomic number. So He42, when it is emitted alpha nucleus, you get Y under nucleus. It becomes A minus 4, Z minus 2. Means atomic number decreases by 2 times and mass number decreases by 4 times. So here you take here uranium 23892, that gives He42 plus thorium 23490. So this is how alpha radiation takes place. Beta minus decay, or how beta decay takes place. Suppose I take phosphorus 3215 and here beta decay takes place, means here in beta decay it gives sulfur 3216 plus E minus 10 plus positron, because here neutron is being converted into a proton plus E minus 10 plus, this is known as antineutrino. So in beta minus decay, the atomic number increases by 1 time. So this manages, so 16 minus 1, 15. So because neutron is a proton plus E minus 10, it is beta decay, electron plus antineutrino. Next. Beta plus decay, suppose I take sodium 2311. So in plus decay, this gives neon 2310 plus E plus 10 plus nu, because proton is getting converted into a neutron plus E plus 10 plus neutron. This is known as a positron. This is known as a neutrino. So here what happens is, in beta plus decay, the atomic number decreases by 1 unit of radium is 1600 years. Now, when 1 gram is reduced to 0.125 grams, how much time does it take? So it's as simple. So 1 gram, how many years? 1600 years. So 0.5 grams, 3200 years. 3200 years. So again half of this 0.25 grams. So it takes 6 plus 1600 you have to add. So for 1 gram it is 4800 years. Next, for 0.125 it takes 6400 years. So this is one problem. Isotopes. So they have same Z but different N, different number of neutrons. So these are no isotopes. So I take here carbon 12/6 and carbon 13/6. So neutrons difference is there. Next one is isobars. Having same same A value but different Z. So I take here, so nitrogen 14.7 comma carbon 14.6. So this is isobars. Neutrons and protons, there is a force. So these are nuclear forces. So there are some properties for this. So first property is they are independent of charge. Second property is it is an attractive force. Third property is they are short range forces. Fourth property is they may exist between Nn, Pn and P and P. And here we have some forces. So these forces can exist up to a certain range and they are non-conservative forces.